Many years ago, I began to think about what it would mean for the universe to have an infinite scale. That is, what if there are infinitely many regions of spacetime larger than the observable universe, and infinitely many regions smaller than quarks, electrons, and photons? Pursuing this idea has led me to an alternative interpretation of physics, which I don't think anyone else has fully described yet. A general description would be that the universe is local and real, and isn't just infinite in size, but also infinite in scale. That spacetime is real, and on a fundamental level, everything is just motion. While these aren't new ideas on their own, I haven't heard this exact interpretation discussed anywhere else before. I think this is largely due to people not fully considering the idea of an infinite scale, as it is central to this interpretation. Now, the purpose of this series isn't to revolutionize physics, or anything like that. I fully admit that this is all just speculation, and is most likely wrong. I just want to share this idea because I think it might be thought-provoking, or at least a little bit entertaining. But to be clear, this series isn't science and shouldn't be taken as educational. It's just some speculation about how the universe could potentially work. As such, I hope that you will also approach this with a heavy dose of skepticism. Because it's an undeniable fact that the current standard model of physics, as described by general relativity and quantum mechanics, is already extremely good at explaining the universe and at making accurate predictions. It's just good science. So I won't be arguing that the standard model of physics is wrong or that physicists are bad at doing science. What I will try to argue is that the scientific evidence which currently exists could be interpreted to support this local and real model of the universe. Not that this interpretation is true, only that it hasn't been falsified yet. Which I think makes this an idea worth exploring, especially because there is definitely something missing in our current understanding of physics. While general relativity and quantum mechanics are great at describing their respective parts of the universe, they don't currently work well with each other. How and why the universe transitions from being described from one set of laws to another is currently unknown. So it may be worthwhile to pursue some alternative ideas, if for nothing else than to poke and prod at the edges of our current understanding in an attempt to hopefully learn something new. Because if I'm right, and there is a hole in our current understanding of physics that could fit a local and real hypothesis through, then it may be something worth discussing. Even if only to strengthen the current non-local models by plugging this gap. So I hope you will stick around and listen. I'll start by trying to explain who I am and why I decided to create this series. Well, I'm a nobody, and you shouldn't believe anything I have to say about physics, as I don't have any formal training or experience with the topic. While I do have a degree in biology, that isn't useful or relevant here. So why am I here trying to describe some new theory of everything then? Well, to be perfectly honest, I didn't start out with this project in mind. I just sort of fumbled my way into it. Originally, I just wanted to make short videos on topics of science that I knew something about or had some opinion on. You know, to educate and entertain and maybe make a little money on the side. However, the market for such content is pretty saturated right now, so I felt I should start with a few topics that had the potential to stand out. While I know more about biology, particularly regarding intelligence and consciousness, something which I plan to do a whole series on eventually, I don't believe it has the same draw as topics about physics. So I decided to start with a short video explaining why, if the universe has an infinite scale, it would mean that time would be relative between observers who exist at two different scalar locations. Essentially, time would move faster at smaller scales relative to larger ones. And conversely, time would move slower at larger scales relative to smaller ones. Which isn't really a new concept or anything. It's well known enough to have been used as a narrative device in science fiction stories for at least the last several decades. However, I have very rarely heard anyone make a formalized reason for why this could be true. The only reason I have any thoughts on the topic is that as a teenager I used to have bouts of insomnia. Instead of getting any sleep, I'd spend the entire night thinking about some topic. On one of these nights, I asked myself, what would an observer the size of the universe who is outside the universe see if they were looking at the universe? This got me thinking about the nature of an infinite universe and how it would all work. So going into this project, I just thought I had something that was rarely discussed, that might be a little bit interesting, that could be made into a short 15-minute video. However, I always tried to take the science seriously, so I went and did some research to make sure that I wouldn't just be talking complete nonsense. and almost every physicist I found dismissed this as a possibility. The scientific consensus is, by and large, that not only is the scale of the universe finite, but also scale invariant. This means that the properties of the universe don't change with scale. So even if an infinite scale did exist, time would not be relative between different positions within it. Which I initially took to mean that I was just flat out wrong and should probably just move on to another topic. However, I still wanted to know how they came to this conclusion, in part to know how I had gotten it so wrong. So I kept searching. And I found that part of the answer comes down to the opinion that the field of quantum mechanics is studying the smallest possible scales of the universe. That there is a definitive floor to reality, and quantum physics is an attempt to understand the smallest, most fundamental unit of that universe. Something about this didn't sound quite right to me. But, even if I didn't like the answer, I couldn't deny that all the experiments were sound, and all the results appeared to support this conclusion. So I almost gave up entirely. But before that could happen, a possible alternative solution fell into place. While listening to a talk on dark matter, I was struck by the possibility that not only does the universe have an infinite scale, but that space-time is real. This immediately led to a model of the universe that is both local and real, and where on a fundamental level everything is just motion. And the thing is, very little else would need to be assumed to exist, and only a few changes would need to be made to the standard model for this to work. Largely, this just comes down to whether or not there is a bottom floor to reality. And this is how I fumbled my way into creating a possible theory of everything. So after months of research, this 15-minute video had exploded into basically everything that will be presented here. But to reiterate, I am not a physicist. I can't claim that anything presented here is fact. I can only say that this may be thought-provoking and possibly a little entertaining. Core to this interpretation is the idea that the scale of the universe is infinite. To introduce the concept, I'll explain the thought experiment I just mentioned. What would an observer the size of the universe, who is outside the universe, see if they were looking at the universe? This is what I came up with that sleepless night all those years ago. To begin, my real passion is in biology, so I was really only interested in the physical properties of the observer's vision. That is more or less how I arrived at this question in the first place, by wondering about the perspective of not only other people, but of various animals as well. This thought experiment was just an attempt to push the boundaries of this line of inquiry as far as it could go, which meant that I was not at all concerned with what the universe actually looks like or how it's structured, but rather the experience of the observer. This means I will not try to assume any new physics or properties of nature. The second thing to note is that this question is full of variables. Just about every part of it can have multiple interpretations that will completely change the answer. Like, what even is an observer? All that I meant was just someone or something that can make an observation. So it could be a person, an animal, or even some mechanical device or robot. Just so long as whatever is chosen can make some kind of observation of the environment around itself. For this explanation, I'll just go with a person who is visually observing the universe. Then there's what it means to be the size of the universe. While there isn't a definitive answer yet, what evidence exists could support a universe that is infinite in size, which would mean that our observer could potentially be infinitely large. But to prevent this from becoming too complicated, we'll just stick to some quantity that is known and say that our observer is the size of the observable universe. This is an approximately spherical region that is 93 billion light-years across, centered around the Earth. It encompasses everything that we can observe from our position on this planet due to the expansion of the universe and the properties of light. There is definitely more to the universe beyond this limit, as this is just the region of space that we can currently see and observe. This limitation also helps to answer what it would mean to be outside the universe. In this instance, the observer isn't outside the universe as a whole. They're merely outside the region of the universe that we can observe. And because I don't want to make any assumptions about what exists beyond our knowledge, we'll only be considering how the observer views the observable universe and try not to assume anything about what's beyond this region. At least for now. But there's still the question of how the observer is positioned. They could be moving away from Earth, possibly due to the expansion of the universe. Or they could be moving towards us at some velocity. Whatever we choose will have an impact on what the observer will see. For now, we'll just keep them at a constant distance from where the Earth currently is, which is the central point of our observable universe. The observer will always stay a fixed distance away from this point for all of time. It isn't necessary to decide on an exact value for this distance at this moment, so for right now, I will just leave it undefined. Just imagine the observer some length away from where the outermost layer of the observable universe is today. So something more than 50 billion light years away from where the Earth currently is in any direction. With that all out of the way, we can finally start to answer what the observer will actually see. And this is where focusing in on the observer and not the universe itself begins to matter. Because the act of making an observation requires some physical process to be carried out. In order for the observer to see anything, a signal of some kind, like a photon, would have to be physically received and then processed in some manner. For our human observer, this would mean that a signal would have to enter and travel through their eyeballs to the cell on their retina. These cells receive that signal and then send other signals through a network of other neural cells towards the brain. These signals would then have to spread out through the neurons in different parts of the brain in order to be processed as an image. But this observer is 93 billion light years tall, meaning their head would measure around 12 billion light years long. So every signal from a photon would need to travel some billions of light years from the time it enters their eye before the observer processes that information. Since I'm not assuming any new laws of physics, then the transmission of this information would be capped at the speed of light. Meaning, it would take billions of years from the time a visual signal enters their eye to the time it is mentally processed by the observer. Under the conditions of this thought experiment, this process could be as long as the time it took to go from the Big Bang all the way up to the present day. Of course, for the observer to be able to understand and comprehend these visual signals would require other regions of the brain beyond the visual cortex to be stimulated, which could add at least millions, if not billions of years to the processing time depending on what assumptions are being made. Like how much time does it take for each cell to process a signal before it transmits its own? Because the cells within the observer would be about the size of a solar system, meaning it would take around a year just for a particle of light to travel across each cell if it were unimpeded. But for cells to function, chemical interactions need to take place, including when processing and transmitting a signal. At this size, cellular activity would take some considerable amount of time to occur, slowing down the entire process. All of this would mean that the observer would see our universe moving faster and experiencing more time than themselves. In order for the observer to process a few seconds of visual information in their frame of reference, some millions to billions of years could elapse at our scale on Earth. But things get more complicated when we recognize that the matter in the universe is moving. The observer is not looking at static objects. And since they are locked a certain distance away from Earth, it means that eventually, the outermost galaxies of the observable universe would appear to be moving towards them faster than the speed of light. This doesn't immediately violate the laws of physics because the galaxies themselves aren't actually traveling this fast. Instead, the amount of space-time between these galaxies and the Earth is increasing due to the expansion of the universe. So only the distance between the Earth and the furthest galaxies increases faster than the speed of light. However, I said that the observer is a set distance away from the Earth, which means that they will have a similar relative perspective as us, where the outermost galaxies of the observable universe would appear to be traveling faster than the speed of light towards them. So a galaxy that would be moving towards our observer would be traveling at an increasingly faster rate than any light that it emits, meaning that light emitted from galaxies when they are closer to the observer will be seen by them before any light emitted when the galaxy was further away. So the observer could see the galaxies pop into existence in front of their eyes before they begin to travel away from them, backwards in time. The observer could therefore not only see the universe moving faster and experiencing more time than themselves, they could see some cosmological objects out of sequence in time. There's a lot more that could be explored with this line of inquiry, especially as we consider what would happen if the observer were moving through spacetime relative to the Earth. But I want to get back to the experience of time being slower at larger scales, because it's possible to imagine that our observer is even larger than the observable universe. After all, the universe may be infinite in size. As we increase the size of the observer, the effect of this experience becomes even more pronounced. For example, the observer could be so large in scale that the observable universe is the size of a grain of sand relative to them. meaning they'd be some hundreds of trillions of light years tall. The observer's head would now be some trillions of light years long, and the cells in their body are now as large as entire galaxies. Depending on what assumptions are made, it's possible that the observer would experience our universe as some kind of large firework that expands into large bursts of shimmering lights before fading out into nothingness with time. A thing that only exists for a brief moment from the perspective of our observer. Of course, there's two problems with everything I've said up until now. For one, this only demonstrates that the experience of time could be relative between two observers at different scales. Because so far, I've only discussed the physical process of making an observation. This does not mean that time itself is relative, only that the experience of time changes with scale. And second, our observer isn't made of anything tangible or real. We have conceptually increased their size, but there aren't particles big enough to construct their bodies. So they can't be made of anything. To try to correct both of these issues, let's push this thought experiment to the limit of our current knowledge. What if the observable universe were the size of the Planck length relative to the observer? The Planck length being the smallest possible distance that we could ever make an observation of. This starts to solve a few problems. For one, since the Planck length is the smallest scale at which we could ever potentially observe, it implies that if we've measured something, and it has some measurable size, then it should be larger than this distance. In other words, if quarks and electrons have a size, then it must be something larger than the Planck length. So the observer would be made out of particles that are larger than our universe. In this setup, the largest scales of our universe turn into the quantum fluctuations of the larger scale universe of the observer. Reality probably doesn't look exactly like this, however. Even if larger scale universes were possible, the distance between our universe and the next largest scale could be even greater. But at least it gives us some plausible material that our observer can now be made out of, which are particles and fields that are larger than our universe. Of course, this means that they could no longer view or measure our universe in any meaningful way, as the Planck length is the theoretical limit to our ability to measure reality. So at most, our universe would look like some small part of a fraction of a second of some quantum fluctuation to the observer at their scale, which is kind of interesting. But more importantly, under this setup, they can measure and observe their own scalar universe and the particles they are made from, because they would basically have the same view of their universe as we do our own. So if they try to do something like find the value for the speed of causality, it would be done using the electromagnetic fields that exist in their scalar universe. And if we assume that their universe functions like our own, and that they exist on an Earth-like planet with a similar rotation and orbit such that they have a comparable unit of seconds, and that they use a relatively similar meter as our own, then they should get basically the same value that we do, roughly 300,000 kilometers per second. But the units for this measurement would be scaled to their universe. The meter would be physically larger than our own, but their second would last much longer than ours. So the absolute value of the speed of causality would be different in the observer's universe. Or put another way, the speed of causality is faster at smaller scales and slower at larger scales, which would mean that the speed of causality would be variable with an infinite scale, where more time passes faster at smaller scales relative to larger ones. And the same would be true for all the constants of the universe. The observer would be measuring some corresponding part of their universe, which would contain more mass than its counterpart at our scale. So their results would be scaled to their universe, meaning that the properties of the universe would be measured and experienced differently when comparing two observers at two different scales. The laws of the universe don't change. It's just that observing the universe from different scales changes how different parts of the universe look relative to each other. And this isn't because of the observers. It would be a property of the universe itself, because these particles in the observer's universe aren't just larger, they're more massive, which means it would take more energy to move them relative to the particles that exist at our scale. Not only that, but the fields and waves around these particles would also be scaled with the observer, meaning they too would be larger than the fields and waves generated by particles in our own universe. Which is what changes in scale would actually mean. That even if the laws of nature stayed the same, then two proportionally similar things that are separated by scale would still have different properties when compared to each other. If the universe was completely empty, except for two wavelengths that existed at two separate scales, then it should still be the case that they would have different energy contents and would experience time differently. And all of this came about without needing to make many assumptions about the new physics or new entities in the universe. It's just a consequence of the physical laws we already have if we assume that the scale of the universe to be infinite. But if the universe is infinite in scale, the observer could be even larger. So they can go to an even larger scale, above the one that's larger than ours, and they could keep doing this an infinite number of times. And this is just the start of what exploring the idea of an infinite scale to the universe can lead to. This series will explore what else this could possibly mean for our understanding of the universe, especially if we make the assumption that space-time is real, as it results in a very specific interpretation of physics that is local and real that I'd like to describe. A 7-part video series about an idea that I admit is probably wrong may seem like a bit much, but I really did try to be as concise as possible. The problem is that there's a lot of information I need to cover, because most physicists appear to think that all local and real hypotheses have already been falsified. And while a consensus opinion has yet to form, most physicists believe that the universe has a finite scale, at least at the Planck length. Basically, most physicists would probably say that every part of this interpretation is wrong. So I found it necessary to spend some time justifying this idea and why it should be considered. Here's an overview of how this series will be organized. The first 2 videos that follow this introduction will be devoted to countering the idea that such an interpretation has already been falsified and ruled out, starting with why local and real theories are still possible. This will be done by talking about Bell's inequality theorem and all related experiments. These are the most common demonstrations for why the universe is non-local, and one of the biggest reasons for why local theories are almost always ignored. I will explain why these experiments only rule out certain types of local theories, which does not include the one I will be describing. The third video will explain why it's possible for the universe to have an infinite scale. I will discuss the evidence used to demonstrate that limits exist in the universe, and will attempt to show that this view may not be very strongly supported. After this, the fourth video will describe the actual details of this interpretation. That is, a local and real universe that has an infinite scale, where space-time is real, and everything can be described as motion. I will explain the reasoning and possible mechanism for this. The following 2 videos will then go into the implications that would result from this interpretation. Starting with the 5th video, which will discuss a possible explanation for dark matter, which is that it comes from motion and interaction. The 6th video will offer comments on what this would mean for the standard model of quantum mechanics, which will be that quantum mechanics is good science, but possibly incomplete, kinda like that quote from Einstein. The major incompatibility being that quantum mechanics assumes that there's a floor to reality, that there's a smallest possible scale. I will argue that this assumption can be removed from quantum mechanics while leaving almost everything else intact. The only major change is on what the quantum fields really are. And the final video will just be a quick conclusion where I wrap up all these ideas that were presented and offer some final comments. I hope that you will stick around and watch, and that you find this at least mildly interesting.